Are you ready to go? I'm saying that because all of the lectures at this seminar, this workshop, will be recorded for posterity in video. The speakers will become stars of the internet. But I'm David Wallace, I'm the director of the Newton Institute, and I'm really pleased to welcome you all to this workshop. It looks fantastic. Of all of the workshops that have been held in the last 18 months since I arrived, this is the one which is actually closest to my own personal interests as they were. And unfortunately, I've just managed to organize 3 days in London, so my life at the moment. But it does look a great conference. I'm sure you'll have a great time here. A few nuts and bolts things. You came in through one door. There are two other doors. If there's an emergency of any kind, just leave through these doors. The other thing that I would ask, there's quite a few people in the room. Please no trailing wires. Be very careful about trailing wires in the Institute because we don't want people tripping over them and falling downstairs and all the rest of it. A second thing on nuts and bolts is really just about the staff in the Institute. The staff here, I believe, do a great job. People really appreciate that. They are here to help you. If you have any query, don't hesitate to ask them. Their role is to make your stay here as pleasant and effective as possible to enable you to do the science that you want to do. If there's any query whatsoever that you have, just ask at the reception desk and they'll do their very, very best to help you. A word of thanks, really, from me, of course, to the organizers of the whole program, but particularly to Bertrand and to Philippe for the organization of this workshop, because without your efforts, guys, it wouldn't take place. And as I say, it looks really interesting. So at this point, I'm going to have to leave you. I'm sure you will have a great week. It's the first of my visits to London, so I'll have to leave you to get on with it. But I don't know if Bertrand or Philippe was going to say a few words at the beginning, just before the talk. But thank you all very much and welcome. And excuse me.
Good morning. So we are the two organizers, Philippe Francisco and myself. So I think you already are all set, ready to listen to the first talk. So start. So Bertrand Eynard.
Hello, can you hear me? Yeah. So hello everybody. Well, it's a great pleasure to be invited at this conference and in this great place where even restrooms have blackboards. So my talk today will be about, I will talk about a method, an algebraic method, which applies to several problems of combinatorics and statistical physics or even high energy physics. So you see I've displayed some Riemann surfaces, some partitions or crystal growth model, and this diagrammatic equation. What I'm going to talk about is this diagrammatic equation, which in fact defines some algebraic quantities, and which I will explain. And I will show some applications of these diagrammatic equations for instance, for counting surfaces like Riemann surfaces, or for counting generating functions for those partitions. And I will try to focus more on the partitions today. So, so I will start by giving the definitions of those algebraic quantities with that diagrammatic equation, and I call them symplectic invariants. Well, I don't know if it's a good name or not, but because they have some symplectic invariance property, of course. And so I will give the definitions associated to a spectral curve, and then I will discuss why this definition is interesting and some of its applications. So among applications, there is matrix models, because that's where I first discovered those things. in matrix models, and how you can they can be applied. Some of their applications allow to count surfaces like triangulated surfaces, discrete surfaces. Another application is counting Riemann surfaces, measuring the volumes of module spaces like intersection numbers or Weil-Petersson volumes. Another application which I will try to focus on today is counting partitions, which is a kind of model for a growing crystal or for the totally asymmetric extrusion process. And also some of partitions have applications in algebraic geometry or topological string theory through Gromov-Witten invariance. And then I will conclude. So the definition. So I will define those algebraic, symplectic invariants, and they are associated to what I call a spectral curve. Well, there is a definition of spectral curve in integrable systems, and it's not exactly the same thing. Nearly, it's closely related, but here is a definition. So a spectral curve for me is just a plane curve. So a curve which you can draw in the xy plane. Well, in fact, x and y are complex, but I draw only the real section. So it's given by, and it's this curve, this plane curve, is written parametrically. So by two functions, x of z, y of z. And in this talk, I will assume that the parameter z lives in the complex plane. So it's two analytical. So my spectral curve is the data of two analytical functions of z. And I will assume today that z lives in the spectral, in the complex plane for simplicity. I could take any other Riemann surface for z, but it will make the presentation more complicated. So that just means the curve is of genus 0. But any genus, but the same definitions can work for any genus. So the spectral curve is the blue curve here, and there are some special points in the spectral curve which are the branch points. Branch points are points where the tangent is vertical. So that is x prime equals 0. And I will assume that all branch points are regular branch points. That is, that near branch points, the curves behave locally like a square root. Y behaves like square root of x. So this is an assumption which I make. This is what I call a regular spectral curve. So all branch points, near all branch points, y behaves like square root of x. So that means that near a branch point, there are 2 points on the curve with the same x image, with the same abscissa x. So there are 2 points which I call z and z bar with the same x. X of z bar equals x of z, and I call z bar the conjugated point of z, but it's defined only locally near branch points. It's not defined globally in general. But that's all what I need. So this is the spectral curve. Now there is one more thing I need about the spectral curve. I call it the recursion kernel. So this is this quantity. The details are not very important, but see that the functions x and y enter here. There is this y of z minus y of z bar times x prime of z bar. And this part does not depend on the parameter z1. And z1 enters only through this part here. So it has a simple pole with residue 1 at z1 equals z, and simple pole with residue minus 1 at z1 equals z bar. And it is symmetric if you exchange z and z bar, this quantity. Well, nearly. Well, normally you need to make it a differential form, and then it is symmetric. So this is just a definition. The details are not important. The only thing I want to convince you about is that if x and y are explicit functions, then this is a very explicit quantity, and you can really do computations with it. Explicit computations.
The notion of z and z bar is only defined with respect
Yes.
to branch bound.
Yes. Yes.
Yes.
So this recursion kernel is also defined only locally near branch points in the variable z. In z1, it's defined globally. So then I will define correlation functions, endpoint correlation functions of some order G, and G will be associated in most applications to a genus. So I call G the genus. So the 2-point function to genus 0 is defined as follows. It's just 1 over z1 minus z2 to the square. So again, it's very explicit. It cannot be more explicit. And, but in fact, this is known as the Bergman kernel of the complex plane. Well, for the complex plane, it's, you don't really need such a name. But imagine instead, if z lives not in the complex plane but on the torus, you would replace this by the Weierstrass function of z1 minus z2. And if it lives on a more complicated Riemann surface, it would be the Bergman kernel. But again, it's very explicit. The Bergman kernel is just the second derivative of a log of a theta function. Then I defined all the other correlation functions recursively by this equation. So the variable zn plus 1 appears only in this recursion kernel, k of zn plus 1 z, times other correlation functions which were defined at lower level of a recursion. And you take residues at all branch points. So again, this equation is very explicit, in fact. And the best way to understand it is diagrammatically. So you represent the endpoint function with like something with n legs. Well, in fact, here it's the n plus 1 point function, so with n plus 1 legs and genus G holes. So, and the way you compute it recursively is as follows. So Zn plus 1 appears in the kernel K, so you draw a propagator from Zn plus 1 to Z, with the propagator is K. And then you plug to this propagator some correlation functions which were already defined recursively. So there are two types of terms here. One is the n plus 2 point function with genus G minus 1, and two of the variables you see are Z and Z bar. So you have all the same, you have the same variables here, Z1 up to Zn, and also Z and Z bar. And so you just put, link them to this vertex. And the vertex means that you have to take integrals over the variable which is at the vertex, so the variable Z. You have to take integrals which are residues at all branch points. So it's just a contour integral. And the other term is you split the genus into two parts, H and G minus H, and the variables Z1, Zn into two subsets, J and its complementary J bar, and in all possible ways. And it's a very easy computation. Every correlation functions which appear there are rational functions, and it's very explicit. I mean, if x and y are explicit functions, all those equations give very explicit computations and can be computed, well, to lower genus by hand. And so then the correlation functions which are here are computed recursively by the same recursion until you reach W20, which is the Bergman kernel. So what it gives, for instance, so here's some examples. So for instance, the 4-point function genus 0, you need only 2 steps in the recursion, and you get this sum of diagrams. So the arrowed edge here is a K kernel, and the non-arrowed edges here or there are those the W20, so the Bergman kernels. So here, for instance, you have 2 K kernels and 3 Bergman kernels, and you have to take the sum over all ways of exchanging the variables there. And so it's you just need to take 2 residues, one there, and you compute it. It's rather explicit. Another example, the 1-point function to genus 2. It's a sum of 3 graphs with 2 loops. Genus 2 is associated to 2 loops. Well, the number of loops is the genus. And again, for instance, here each arrowed edge is a K propagator, here or there. And each non-arrowed edge, for instance, this one, is a B, a kernel B, so the Bergman kernel. And for instance, this 1-point function to genus 2 can be computed by hand in most examples, if x and y are sufficiently simple. Well, then I need something else, which is the 0-point function. So W0G, which is usually called FG. And so this means that I have to define a way to contract the legs. And the way to contract the legs is the following. You just multiply, for instance, W1G by a function by the function phi of z, which is just the primitive of y times x prime. So again, very explicit. Take the residue at all branch points and divide by 2 minus 2g. This is the definition for g larger than 2. There are similar definitions for f0 and f1, but they would take more space on the screen, so I won't write them. But for instance, f1 can almost always be computed by hand, very explicitly. f2, well, yes, by hand if you're not too lazy. And even f3, probably, I'm too lazy to compute f3 by hand, but those definitions are very simple, so you can put them on your computer, and it gives you up to, I've computed, for many models, I've computed up to f7 within less than half an hour on my computer. So for the moment, these are only definitions. So you have a spectral curve, and you compute their correlation functions and their FGs. So what is this definition useful for? Well, one of the reasons this definition is useful is because it has many nice properties. So the first property, which is not obvious from the definition, is that all those correlation functions are symmetric in all their variables. It's not obvious because the definition was not symmetric. There was the variable zn plus 1, which seemed to play a different role. But it is symmetric. It can be proved by induction. It's not complicated. And this symmetry is, in fact, a hint of integrability, because somehow this proves that this two-point function is somehow the second derivative of something. Well.
It's good also in the set of diagrams that you have, that there is, if you want to pivot one.
Yes, exactly. You can. In fact, it is proved diagrammatically. You can prove this symmetry diagrammatically by. Well, the only thing you have to do is exchange the order of residues. So you just pick up a residue and it works. So this is one property. Another important property is symplectic invariance. So if you take two spectral curves represented by the two functions x, y, and x tilde, y tilde, if the wedge product dx wedge dy coincides with the wedge product dx tilde, dy tilde up to a sign, then they have the same FGs. They don't necessarily have the same correlation functions, but they have the same FGs. This theorem is not easy. I mean, it's not proved just diagrammatically. This one is the difficult one, but it has many applications. The main application is that if you have two different models with two different spectral curves, in most examples I know, it's very easy to compute, to see if they have the same FGs, because most often the symplectic transformation from one spectral curve to the other is completely trivial. And for instance, one of the applications is in conformal field theory. If you want to compare the PQ minimal model and the QP minimal model, the duality is just the exchange XY, so it's trivial here. And for instance, another application is the Witten-Kontsevich theorem. You compute the spectral curve of the two sides of the Witten-Kontsevich theorem, and there is an obvious symplectic transformation which transforms one into the other. And again, it's just the symmetry XY, the exchange XY. Another important property is taking limits. Imagine you have a one-parameter family of spectral curves such that at t equals some critical time tc, the spectral curve is singular. Singular means that instead of having, there is a branch point which instead of being a square root is now a cusp. Typically, imagine that imagine that y behaves like x to the power p over q as an example. So at this singularity, y behaves like x to the power p over q. So then the FGs will diverge at this point. But if you want to compute their leading behavior when they diverge, near the critical point, well, what you have to do is choose t very close to tc. So the singularity is resolved. The curve is no longer singular. You enlarge this region. You blow it up. So this is the blow up of the curve. And so the enlargement of this, if you zoom this small region, you get a new curve, which you call x tilde y tilde, which is another spectral curve, and which basically depends only on the exponents p and q. So it's universal. So you get a kind of universal curve. And the theorem is that the way fg diverges is t minus tc to some power times the fg of that curve. So basically, all limits are extremely simple to take. And for instance, it works, in fact, even if it's not singular. This works not only for the fg's, but also for the correlation functions. And for instance, if you take just the vicinity of a branch point, so that would correspond to p equals 1, q equals 2. The blow up of the curve is just the curve y equals square root of x. And the correlation functions of that curve are the one given by the Airy kernel. And it's just basically you recover Tracy-Widom law. But it works for any types of singularity. And for the PQ singularity, you recover the PQ minimal model in general. So Tracy-Widom is just the 1-2 minimal model. So another property which is important is integrability. If you compute this formal series, sum over g of n to the 2 minus 2g fg, this is just a formal series. Take its exponential, and this is the exponential is a tau function. It obeys some iota equations. There is a
function of E.
Excuse me?
It's the function of E.
Of the spectral
E.
curve,
Ah,
yes. Yes, well, I mean, if the spectral curve depends on some parameters, it's a function of, and it's also in the variable n. So it obeys iota equations order by order in n, because it is a formal definition. I mean, it's not necessarily convergent. And in fact, there are also determinantal formulae for the correlation functions, also formally, I mean, in a formal sense, order by order in n. But I don't want to enter the details. And there are many more nice properties. For instance, there are formula for all derivatives with respect to any parameter of a spectral curve. There are nice properties for modular transformations, the so-called holomorphic anomaly equations. I don't know if you've heard about them. So those FGs and the correlation functions have many nice properties. But now let me study their applications. So they were first found in matrix models. So consider a matrix integral. So with a measure dm e to the minus n trace of v of m. So where m is a n by n matrix, and assume that it has an expansion of that type. So exponential of sum of n to the 2 minus 2g fg. So this is, I mean, not every matrix integrals have such an expansion, but if you assume that they have, you want to compute the fg's. Well, there is another way. There are also formal matrix integrals, and for formal matrix integrals, this expansion exists by definition, but it's just formal series. And again, what you want to do is compute the fg's explicitly in terms of a potential v. And the theorem, which is obtained just, you write the Schwinger-Dyson equations for that integral. And the Schwinger-Dyson equation in matrix models are called loop equations. And just by solving loop equations recursively in powers of n, you obtain that those fg's are the fg's, which I have defined, of some spectral curve. And the spectral curve, as you see, is just basically x and y are two rational functions with coefficients gamma, alpha, uk's, and the gamma, alpha, uk's are related to the potential v by this very simple algebraic equation. It's rather explicit. You don't need to see the details, but just the uk's are somehow a reparameterization of v. So it's quite explicit. Well, the only thing maybe I want to comment on is here I've written the ensemble of matrices Hn of C. And this is not the set of Hermitian matrices. This is the set of normal matrices with eigenvalues constrained on the path C in the complex plane. And the nice thing is that Schwinger-Dyson equations are completely independent of the path of C. So basically, it works for any C, not only the. Sorry?
What is alpha in this equation?
Alpha, you find it from this relation. I mean, if you want this relation to hold, this determines alpha.
You simply assume that V has this form.
You can prove that it has this form. No, sorry. No, sorry. This form is in fact just a subset of. I mean, it works only for some C's because here I wrote a genus zero spectral curve, but the general case has a non-genus zero spectral curve. I mean, the curve has a. You always get an algebraic curve, but with some genus. But in some cases, the genus is zero, and this is what I've written here, just for the simplicity of this talk. But it works in the general case. I mean, the theorem is true in the general case, but.
You have assumed V was polynomial, right?
Yes, but it would work with a much more general class. For instance, V prime is a rational function; it's still of that form, and well, if V is not a polynomial, basically it works. Well, you have an infinite sum here. So another application which I will talk about is counting discrete surfaces. So surfaces made obtained by gluing triangles, squares, and polygonal pieces. And you want to count such surfaces of a given genus. And the way you count surfaces of a given genus is by defining a generating function. And so the generating function you define is basically you put a weight per triangle. So you have this parameter T3 to the power number of triangles, T4 to the power number of quadrangles, TD to the number of d-angles, and so on. You also can put a weight for the number of vertices, and you have to divide by the number of automorphisms. You cannot, in fact, so this is the FG, but you could also define some FGs with some marked faces, which would be the correlation functions. And if you have marked faces, basically there is no automorphisms. Well, there are recursive equations known as Tut's equations, and Tut's equations are just recursions on the number of edges in the discrete surfaces. Tut's equations, you remove one edge at each step, and you find recursive equations, and you can prove that the Tut's equations imply that indeed those FGs are the FGs of some spectral curve, which is there. And again, the UKs are just reparameterizations of the TKs. Yeah. UKs and gamma and alpha are just a reparameterization of the TKs and T. So again, this works for those FGs, the symplectic invariants can be used to count discrete surfaces. And the correlation functions count discrete surfaces with marked faces. In fact, it also works if you start putting colors on the faces. Like an Ising model, you can put an Ising model on the discrete surface, and it still works, but the spectral curve would be a little bit more complicated. Another application is counting Riemann surfaces now instead of discrete surfaces. So consider Riemann surfaces of genus G, and I assume G larger than 2 for the moment, so it's what's called stable surfaces. A Riemann surface of genus G can be decomposed into 2G minus 2 pairs of points. This is a pair of points, where the boundaries of a pair of points are geodesics for the metric, for the Weil-Petersson matrix, which is the matrix of constant curvature. So this is if the genus is larger than 2, the Euler characteristics is negative. And so the Euler characteristic is the average curvature. It's negative, so there exists a metric with constant curvature. And you can cut the surface into 2G minus 2 pieces, 2G minus 2 pairs of points, such that each boundary is a geodesics in that metric. And so for instance, for a surface of genus 2, you have 2 pairs of points separated by 3, so 3G minus 3 geodesics. And the set of, so the Riemann surfaces are completely characterized by the length of the geodesics. And so basically the length of those geodesics give a good coordinate system of the moduli space of Riemann surfaces. Well, this is called, this is used, this is a very old trick of Teichmüller spaces and Weil-Petersson volumes. But so the Weil-Petersson volumes are the volumes of those moduli spaces, so volumes with the metric just the flat metric for those lengths Li. But it's not easy to compute because it's not just the integral of Li from 0 to infinity, because there is more than one way of cutting the surface into pairs of points, and you have to take that into account, make sure that you have not counted the same surface several times, and that's a non-trivial topology, so that's not a non-trivial computation. But I can prove by different methods that again those FGs are the FGs of some spectral curve, which is, you see, extremely simple. So it's x equals z squared, and y equals sine of z, basically. So just sine function. So again, it's very explicit. And well, one way of proving it is observing, in fact, that diagrammatic recursion relation for the correlation functions is basically the Laplace transform of Mirzakhani's recursions on volumes of module spaces. Well, this is one way of proving it, but there are other ways, more like Kontsevich methods with intersection numbers. But it works. So now let me move to the application to random partitions. I will represent partitions rotated by 45 degrees, which probably many of you do very often. So rotated by 45 degrees. And I want to count partitions with the Plancherel measure. So it is a problem studied by many people in different contexts. So you want to compute partitions with the Plancherel measure. The Plancherel measure is just the dimension of so the partition lambda represents labels a representation of a symmetric group which has a certain dimension, and the Plancherel measure is just the dimension over the weight. The weight is the total number of boxes to a square. Sorry, weight factorial to a square. So there is a way to understand this Plancherel measure. It is the number of ways of obtaining this partition by dropping boxes from the sky in a random order and from random locations, and this gives this Plancherel weight. I mean, the number of ways to obtain the same shape here is precisely this one. So this is the Plancherel measure. So this means it can be used as a model of a growing crystal, of a two-dimensional growing crystal. This is the trick used by Spohn, Treyhofer, and many other people like Jansson. Well, it appears in many papers. This is based on the Robinson-Shanstead algorithm. Another bijection, another way of representing this model is related to the totally asymmetric exclusion process. So instead of encoding the partition by the length of its rows, encoded by the projection of the downright edges of this diagram. So the downright edges. So this one is, call it H1, H2, H3, and so on. So they are ordered. They have integer values, and they are ordered. And each time you drop a new box, you see that one of the HIs will jump to the right if the position is unoccupied. So here at t equals 0, so here at each unit of time, time is going from 0 on the top to, and it's going downwards. So at each unit of time, I've represented the position of the HIs, so particles. And you see that at each unit of time, one of the particles jumps to the right if it is unoccupied. So this is in bijection with a totally asymmetric exclusion process. This analogy has been used by many people for a long time. I cannot cite everyone who has worked on it. But basically, in all those problems, what we want to compute is, for instance, the partition function. We are also interested in correlation functions of densities of the HIs and so on. But let's focus for a moment on the partition function, so the generating function, which is just the sum of our partitions with the Plancherel measure, and with the Poissonized version, which is the grand canonical ensemble. So you allow any number of boxes and put a weight per number of boxes. So q to the power 2 times the number of boxes. So you want to compute that partition function, and you are especially interested in the large Q limit, because you see Q, this parameter Q is coupled to the number of boxes, and you are interested in the limit of a large number of boxes. So large number of boxes, so the asymptotic limit of a large number of boxes, and the number of boxes is more or less Q square. So you are interested in the so we are interested in the large Q limit of that. And so it can be proved, but for the moment, let us assume that log z has a large Q expansion of that form. So sum of Q to the 2 minus 2g fg's. And you want to compute the fg's. Okay? And well, you guess that there will be a spectral curve associated to it. But for the moment, let me say that we can also be interested in something a little bit more general, where we also put kind of Boltzmann weight for the CKs, which are the Casimirs of lambda. And the Casimirs are basically the sum of HIs. The kth Casimir is sum of HIs to the k, to the power k. And so we put parameter tk times ck, and we rescale by an appropriate power of q. Sorry, the HIs are those projections of downright edges here. So this is what we'd like to compute. So
you mean that the sum is infinite, but you subtract the one for the empty diagram, something like that?
Yes, well, there are a few subtleties which I've left. Well, I mean, it would take too much space to explain, but well, the Casimir is not exactly that. There is minus something which depends on the size, but indeed, that's what I'm going to do. I'm going first to put a bound on the number of particles, and then let that bound go to infinity. So the Plancherel measure can be written in terms of the HIs. It's just the van der Waals square of the HIs divided by the product of HI factorial to the square. So this is just a rewriting of the Plancherel measure. And the fact that there is this van der Waals square makes a very strong analogy with matrix models. But in fact, it's more than an analogy. It's really a matrix model. And so there is this Q to the lambda, and you could also add the Casimirs, which I don't write here. So first, so this is a sum over integer values of HIs. This is a discrete sum where HIs take integer values. But there is a standard trick to transform that into an integral, a contour integral. You just consider this function f of h, which is pi to the its exponential I pi h divided by sine of pi h. So it has simple poles at all integers with a residue plus 1. So if you take a contour integral with that function, it transforms an integral into a discrete sum with integer values. So you just do it here. So if you consider this integral of all the dh1, dhn around that contour here, with products of van der Waals square of the HIs times this function f of hi times this this weight here, which is just the same as the weight there. So then, because of this function f, this contour integral is in fact the sum of all of the HIs taking all integer values. It is a very standard trick. But now, so it means that the partition function which is there can be rewritten as a contour integral with a van der Waals square, and it's really a matrix model. And as I said, the Schwinger-Dyson equation for this kind of integral do not depend on the contour. So basically, you apply the first theorem I was talking about for matrix models, and it works. It gives, so it tells that the FGs are the FGs of the associated spectral curve. So the only thing you have to do is compute the spectral curve. Well, there is a little algebra to compute the spectral curve, but there is a kind of a small miracle occurring when you compute the spectral curve associated to this model. It is that this f here contains a gamma function. And here the denominator, which is a factorial, also contains a gamma function. And there is a nice simplification between the two. And so the method works very well because it is the Plancherel measure. I mean, in principle, it could work with any other weight. But because it is the Plancherel measure, the spectral curve is going to be particularly simple. And here it is. So the spectral curve is just the two functions x is just z plus z minus 1, and y is just log z. So basically, y equals arc cosh of z, arc cosh of x, or x equals cosh of y, 2 cosh of y.
Besides the fact that the equations, the Dyson equations are independent of the contour.
Yeah.
There is a special contour in which you can really see that H is like the eigenvalues of the matrix. For example, the vertical axis or something like that, and take some higher out.
Well, no. In fact, the contour is encoded in the genus of the spectral curve somehow. And the fact that it is a genus 0 spectral curve is related to what you say. Well, I mean, it would be to, maybe you can discuss that later. I don't want to discuss the details, but just the point is that the spectral curve you get is extremely simple. And you can also compute it with the Casimirs. So if you want to add the Casimirs, it becomes a little bit more complicated, but still it's very explicit. So the UKs here are just a reparametrization of those TKs coupled to Casimirs. And so the theorem is that the log of the partition function is the sum of, the partition function is this tau function. And in fact, so it works for the partition function, but it also works for densities. So for correlation functions of densities, for instance, the density here, so rho of x is basically the probability that x equals one of the hi's, but rescaled by an appropriate power of q. So this is just the average density of hi's, and so it is also a series in q. To leading order, it's just this function y, and to subleading orders, it's all those W1Gs I was mentioning before. And so it means that you know the leading order, but you know also all the corrections. So this is here the 1-point function, but it works similarly for any number of, for the expectation value of any number of densities at different points, of product of densities. So, so it's very explicit. So here the leading order has been well known for a long time, and all the corrections here can be computed. I mean, the first few corrections can really be computed by hand very explicitly. So the expectation value of the density is related to the so-called profile function of the partitions. You just have to take an integral and you get the profile function.
You have sent the number, I mean the size of the partition to infinity, right?
Yes.
What you call big N.
Yes.
So this big N has nothing to do.
No,
with
in fact, this big N appears beyond perturbation.
Okay.
It does not appear.
This Q, which plays the role of the size of the matrices.
Well, it's coupled to the size of matrices. No, sorry. Q is not coupled to the size of matrices. It's coupled to the number of boxes. It's different.
Right, but if you interpreted this log Z as coming from a matrix model, then Q would be something like the size, right? So the number of eigenvalues.
Yeah. So this big N here, appears beyond. So here, when you want to do this expansion, big N will be in sub-exponential contributions. So I mean, the contribution of big N is smaller than any power of Q.
I guess what I don't understand is the meaning of Q in terms of number.
Well, it's related to the so-called Arctic circle property. It means that basically all the particles beyond a certain level are frozen, so you don't see them. Well, I mean, it can be proved, but I mean, it's something quite standard. Somehow, if you take n larger than the Arctic circle, you don't see it.
There was, however, the observation that it's at least suspicious this q to the 2 minus 2g, which is so similar to the n to the 2 minus 2g of the matrix model.
Yes, but it's not the same. I mean, the expansion parameter needs not be the size of the matrix.
And also, n is integer and q is arbitrary.
Yes.
Q is like the size of it.
No, it's like the size of the partition, the number of boxes. while the size of a matrix, the size of a matrix is the width here, the difference between there and there somehow. And Q is like the number of boxes, so it's not the same thing.
Where is the 0 on your picture?
Sorry?
The 0 of the
Well, in fact, the 0 is at Hn, but you have to rescale everything. Well, the 0 is somehow the leftmost point here. Well, I mean, I didn't want to write all the details because it would take much.
And I'm insisting because I think it's important that when you showed us the exact same formula but for matrix models,
yes,
there was an n to the power
yes,
of 2 minus 2.
exactly.
N was the size.
Yeah, no, in fact, n was the number in front of the potential.
But it was also the size.
It was also the size in the matrix model case, but it's not what is important. I mean, when you solve order by order the Schwinger-Dyson equations, the important is the parameter which is in front of the potential.
Okay. So you say there are two parameters, there's the size on one side.
Yeah. So the expansion is not in terms of the size of the matrix, it's in terms of the coefficient in front of the potential. It turns out that for matrix models it is the same coefficient, but it's by accident. So, you get the spectral curve, the correlations, and so for instance here, this is this profile function for the case where you have no Casimirs. So this is the sum of our partitions you want to compute, and here I've removed the bound. And it is well known that if you don't put a bound on the number of rows, it is well known that this series is e to the q square. It has been well known for a long time, but here we are going to recover that from this computation. And so the spectral curve is just this one, as I said. Out of the spectral curve to linear order, you recover the linear order profile function, which is related to the arc cos, the arc seen in good coordinates, which is well known, which you can find in many works. And so then you compute the expansion in powers of q. And for instance, you can compute explicitly from this spectral curve that f0 equals 1, f1 equals 0, f2 equals 0, and so on, which is just the expansion of the e to the q square. So you just recover that. I mean, it's not new, it's just another way of seeing it. More interesting is when you turn on Casimirs. For instance, here I've put a weight for the Casimir C2. You can compute the spectral curve explicitly, so this u naught here is related to this parameter T2 by this equation. And you compute, for instance, I don't write f0 because it takes too much space, but it's related to a polylogarithm. And f1 is just this log, f2 is this quantity, and so on. And for instance, this is the profile function for to linear order, but I can also compute all the corrections in powers of q, and so on. So this is just examples. In fact, this spectral curve was already found in other works, but where they could prove only the leading order behavior, not all the corrections. For instance, it's in works of Nekrasov, the same curve here. Now let me move to another application, which is again a sum of partitions, but with a Q deformations, a Q parameter deformation, and which have applications to algebraic geometry of the Gromov-Witten invariance. I will not enter the details of what Gromov-Witten invariance are, but somehow Gromov-Witten invariance count. So you have a target space, which is a Calabi-Yau manifold, and you want to compute the number of surfaces of a given genus on a given degree, the number of curves of given genus on a given degree, which you can embed in X and passing through given points. So this number, well, if you have chosen the good numbers, this number is finite, and it's the Gromov-Witten invariance. In fact, Gromov-Witten invariants are not integers; they can be rational numbers because you have again to divide by the number of automorphisms. If there are automorphisms. So, but there is a way to compute those Gromov-Witten invariants, or I mean, we compute a generating function of Gromov-Witten invariants. There is a way of computing those Gromov-Witten invariants through a so-called, when X is a toric Calabi-Yau manifold, there is a combinatorial way of computing them and representing them as a sum of plane partitions. Well, it's related to the fact that basically a rational curve of given genus on given degree passing through given number of points is completely characterized by the number of derivatives which vanish at each of given points, and so it can be represented as partitions. I don't want to enter the details of that, but it has been done for some time. So this partition function can be written as a sum over plane partitions. There is a family, a subfamily of Calabi-Yau toric manifolds, which are called the XPs, which are rank 2 bundles over P1. Again, I don't want to detail that. But there is a subfamily of Calabi-Yau manifolds for which this sum is actually a sum over usual partitions, but with a Q-deformed Plancherel measure. So for this family of Calabi-Yau manifolds, Z is just the sum over partitions with the Q-deformed Plancherel measure and some power of the Casimir C2 on the weight of the partition. So this has been computed for some time, and now what we'd like to do is recover VFGs. So take the log and expand into powers of log Q. So, and again, there is a spectral, so again, we do the same trick. We replace the sum of our partitions here, so the discrete, so integer values for the HIs. We introduce a contour integral to take the sum of those integer values. And again, it's related to a matrix model. The only thing we have to do is compute the spectral curve. So this is the result. So this is the partition function we'd like to compute. So with this Q-deformed Plancherel measure, and we want to compute VFGs. And the theorem is that VFGs are given by VFGs of some spectral curve. So here is the equation of a spectral curve. You see it depends on this parameter P. And Z0 is related to the parameter T. So this is very explicit. And what is funny, I mean, it's not a coincidence, of course, but this spectral curve has already appeared in topological string theories or algebraic geometry. And it has a name, this spectral curve. It is the mirror spectral curve. It is the mirror curve of the Calabi-Yau manifold XP. So it is the mirror through mirror symmetry. So basically the theorem says that the VFGs of XP are the symplectic invariants of the mirror curve. So is this a general statement? So are the generating functions of Gromov-Wheaton invariants always equal to FGs of the mirror curve? Well, question mark. So for XP, I've proved it here. But for general Calabi-Yau manifolds, is this true? Well, there is this conjecture. It's not my conjecture. Basically, it's just a rephrasing of Dijkgraaf-Waffa conjecture in some sense. Well, Dijkgraaf-Waffa conjecture, in fact, does not contain the family XP, but it seems to be a very general statement. And so it's a kind of generalization of Dijkgraaf-Waffa conjecture. So there are strong hints that this should be true in general. But it's not my conjecture again, and the only thing I've done is prove it for the family XP. It remains to prove it for the general case, of course. So this is the end. I will just give the conclusion. So I will just summarize some of the main results. So those symplectic invariants are universal in the sense that they appear in many problems of enumerative geometry and integrable systems. In fact, I did not mention all of their applications. There are many more applications, like counting colored surfaces, as I said, the Ising model on a triangulated surface or something like that. They have also applications to Liouville conformal field theory coupled to PQ minimal models, because when you take this curve, basically it's the Liouville minimal model coupled. The spectral curve is the spectral curve of a Liouville minimal model coupled to Liouville coupled to the PQ minimal model. So one of their main advantages is that they are very easy to compute explicitly. I said, for instance, F2, F3, and so on can be computed within minutes on a computer. I'm not good at programmation, so you can probably do better even. Also, their limits are very easy to take for this blow-up theorem. So for instance, you recover the Tracy-Winham law very easily and so on. Well, so here the applications I've considered is for sums over partitions with the Planchel measure. And so what I've obtained is all the large Q corrections, well, order by order. And so in the Q deformed case, it's you get the Gromov-Witten invariance, and again, very explicit formula for Gromov-Witten invariance. For instance, F3, F4 can be really computed explicitly with this method, and I don't think it could be done before with other methods of string theory before. Now, among the further prospects I'm trying to study at the moment, one is enlarging this method to plain partitions. In fact, it works well, and I'm writing the paper now. I could generalize this to plain partitions, and it works quite well. And well, I've not finished computing the spectral curve, but it looks like it's going to be quite simple again. And also it can be Q deformed to give the Gromov-Witten invariance of more general Calabi-Yau's, because the more general toric Calabi-Yau's are obtained as sum over plane partitions. And another application I'm considering is random lattice loop gas models, like the ON model. And again, it seems to work quite well. Well, I've not finished, but it seems to work well. So thank you for your attention.
Other questions?
Do you recover some combinatorial result about plane partition, the classical?
I'm not at that level yet. I'm not yet at that level, but in principle, probably.
And the partition with some symmetry, you can also?
Yes, in principle I can. I've not done the computation in the most general case, but in fact I can compute plane partitions in principle with any boundary conditions.
Yeah, but symmetry condition?
No, not necessarily. Any boundary condition. Any boundary condition. Symmetric or not.
No, not boundary condition.
Yeah, what is really the direction where it goes? It goes to determine the typical shape.
Yes. The spectral curve basically gives the profile function, which is the typical shape. So. Yes.
Speak louder. Oh, so canyon or open curve?
Yeah. Basically, I believe I'm going to recover the same spectral curve. But in fact, there are some subtleties.
Are there other questions?
I have an easy one, maybe somebody. Sorry, you were telling that the Planchel measure, the typical one without Q deformation, the numerator is the Vandermonde of the traditional Jacobian that you have in the matrix model. And the Q deformation, what is it? There is any
well, it's the you replace just the HIs by the Q numbers. I mean, but it's very standard. I mean, I didn't invent that.
So it also corresponds to some natural measure on
yes. It also corresponds to some natural measure.
If you have some sequence which enumerates something, like some FG sequence, what are the properties that it needs to satisfy to be associated to a spectral curve like that? Seems you can do it.
Well, my guess is that you need somewhere Virasoro structure, Virasoro or W algebra. My guess is that somehow this is some sort of general solution of Virasoro or W algebra constraints. So as long as you have Virasoro algebra somewhere, you will get that basically. Well, that's what I would conjecture. I mean, I've not proved that.
Any other question? If not, we thank you again.